Hello, I am Frits de Mul and I would like to talk about electric dipoles on a thin, long line. This presentation is part of a list of presentations about electromagnetic problems. Electrical dipoles on a thin, long line. We have available a thin line, infinitely long, homogeneously filled with dipoles, and suppose that each dipole has a dipole moment notated with P in Coulomb times meters. The question is, calculate the electric field in arbitrary points around the line. First we have to perform analysis to investigate the situation and the symmetry. Then find an approach to the solution, do the calculations and draw some conclusions. We have a cylinder, infinitely long and thin. And there is a distribution of dipoles and dipoles per meter. Homogeneously, all directions are uniform and each dipole moment is P. We choose coordinate axis. The z-axis is the symmetry axis, and cylinder symmetry implies that all points at equal r are equivalent, even if they are at different z or phi. Assume the field components of the dipole field at some distance in point P are known. Then it means that the dipole has a radial component of the electric field strength as 2p cosine theta over 4 pi epsilon naught r to the third, in which r is the distance between the dipole and point P, and this is in far field approximation. For the theta component we have E theta is P sine theta over 4 pi epsilon naught r to the third. What are the possible directions for the dipoles? We will investigate the field in point P on the y-axis caused by dipoles directed in the direction of the x-axis. Here in the direction of the y-axis itself, and here in the direction of z. Assume we have n dipoles per meter, the dipole density, and we choose point P at the distance yp from the axis of the cylinder. Use the symmetry, and this means that dipole element at plus z and minus z will contribute symmetrically, and we have dipole elements in the line element dz. The dipole elements are dp vectors at plus z and minus z, and dp is n, the number of dipoles per meter, times the dipole moment times the number of meters dz, the length of dz. Case 1. All dipoles are directed along the x-axis. In this case, theta is 90 degrees for all the dipoles. Theta is the angle theta, 90 degrees. This means that the radial field of the dipoles is 0 because the cosine is 0, and the tangential field is dp over 4 pi epsilon naught r to the third because the sine of theta is 1. And we end up with a resulting electric vector in the direction of minus x. When you perform the integration using r squared is ip squared plus z squared, Pythagoras, in this triangle here, and then we arrive at a result of E theta is np over 2 pi epsilon naught yp squared. Now we have the dipoles parallel in the y-axis, and this means that dp and dz has angles theta plus and theta minus, and the field direction of the field contributions are ER plus and ER minus, and E theta plus and E theta minus. And this means that for the plus Z dipoles, the cosine is positive, and also for the minus Z directions, the cosine is positive. And the sine is positive here for this direction, and positive here for this direction. And this means that the resulting vector will be in the y-axis. Let's find an expression for the resulting vector. Here we have the vectors again. The y components are given by, for the ER plus and the ER minus component each, is np dz, that is the p here in this equation, over 4 pi epsilon naught r to the third, times 2 cosine theta, times cosine theta, and that cosine theta is the component along the y-axis. And the theta axis are similar, but with the sine theta instead of 2 cosine theta, and we need the sine component to obtain the component directed along the y-axis, and there is a minus sign because the two theta components are directed towards negative y's. These integrations can be performed using standard integrals of the rational functions. The resulting vector is along the y-axis. The standard integrals are not that easy because we have a third power here, and the cosine theta squared is also given by y over r, so we have y squared over r squared here, and we end up with a power of r to the fifth in the denominator. It's not an easy integration. The third situation is when the dipoles are parallel to the z-axis, case 3. In this case, the unit vectors are directed along these directions, here for the theta and these for the r's. And this means that the dipoles are given by cosine theta is negative here, because theta is over 90 degrees. And here the sine theta, for the minus component, the cosine is positive, because the theta is smaller than 90 degrees. And for the sine, we have the situation that the sine is here positive, because this is the sine of pi over 2 plus theta, and this sign is also positive here. And this means that the resulting vector will be in the z direction. Let's look at the contributions. The z components are given by, for the ER components, is np dz over 4 pi epsilon naught r to the third times 2 cosine squared theta minus cosine squared, because of the cosine in the r component, that's this cosine here, and the cosine of the component along the z-axis, and this is the cosine here, this cosine. And for the sine components, these two here, we have the sine in the expression for the e times the sine for the component, and that's the sine is 2 pi minus theta, is the cosine of 2 pi minus theta, that's the sine. And this means again that the integrations can be performed using standard integrals of rational functions, and the resulting e vector will be directed along the z-axis. conclusions. When the dipole direction is in the x direction, then we can easily integrate the contributions, and we end up with an expression here when they are in the y direction and when they are in the z direction. And theta and r are measured from the dipole in point P. This is the end of this talk. Thank you very much.